Welcome to this next video in the playlist on ring theory. In this video what we're going to talk about is unique factorization domains, which for short are abbreviated down to U.F.D.s, with dots in between all of the letters there. Okay, right, so we'll start off then with what the definition of a unique factorization domain is, and then we'll have a look at some important theorems regarding unique factorization domains to get a feel for them. Okay, right, so my first warning then is that this is quite a difficult definition when you see it for the first time, but you will get used to it and you will grow to understand it. Okay, so definition then of a unique factorization domain. So a unique factorization domain, much like a Euclidean domain or a principal ideal domain, is just a special type of non-zero commutative ring. And as always, we start off with an integral domain. So in all three that we've seen now, Euclidean domain, principal ideal domain, and now unique factorization domain, we're going to start off with an integral domain. Okay, so all unique factorization domains then are integral domains. And now, on top of being a normal integral domain, I'll just recite off what an integral domain means. An integral domain, remember, is a non-zero commutative ring which obeys that special property of integral domains, which is that if you multiply two non-zero elements together, the answer that you get is also going to be a non-zero element of that ring. Okay, right, so that's an integral domain, and now the special property that a unique factorization domain is going to obey on top of being an integral domain is that you can factorize all non-zero elements into an irreducible factorization, a factorization of irreducible elements. Okay, so let me remind you then of the definition of an irreducible element from the previous video in this playlist on ring theory. So irreducible is really important in the next condition that we want a unique factorization domain to obey. Okay, so an irreducible element is a non-zero, non-unit element in a commutative ring. So this obeys for an arbitrary non-zero commutative ring. Okay, so R is not equal to the additive identity, and R is not a unit. Okay, and it needs to be the case, if it's an irreducible element, that whenever you have a product of two other elements that gives R, so whenever R can be written as the product of two other elements of the ring, A and B in this case, that one of these has to be a unit. So A or B must equal a unit. Not both of them, one of them. Okay, the other element, this must then just be an associate of R. Okay, a unit multiplied by R, or something of that form. Okay, so there are only these trivial products that give rise to R, basically, in the commutative ring, if it's going to be called irreducible. These products of a unit with an associate element of that element R. Okay, right, so that's what is meant by being irreducible, that you can only be formed by trivial products, basically. Okay, now, the definition of a unique factorization domain is going to tell us that all the elements of the unique factorization domain, so for all R, which is an element of our unique factorization domain, which we'll call capital R, so capital R is going to be the name we'll give for our unique factorization domain, and the only condition that I'm going to set on it is that it's not equal to 0, okay, then you can write a factorization of this element into irreducibles of the form, so R can be written like so. Some unit out the front, and indeed if R is a unit element from our unique factorization domain, then that unit is all you'll have at the front. So the prime factorization, sorry, not the prime factorization, I shouldn't call it that yet. The irreducible factorization at the moment it should be called, and I'll explain that in a moment. Okay, the irreducible factorization will be fairly trivial there, it'll just be that the unit is equal to the unit. But for all the other elements that are not equal to units, you'll then have some irreducible elements afterwards. So you'll have, let's say, P1, and then it will be raised to the power of alpha 1. So alpha 1 is just the power that it appears in there, so it means P1 times P1 times P1 alpha 1 times. And then you'll have times P2 to the power of alpha 2 here, and it will be a finite product of irreducibles here. So let's go up to Pn here to the power of alpha n. Okay, so this is the definition of a unique factorization domain, that all elements in the unique factorization domain except the additive identity must be writable like this. Okay, where these elements, they're not primes, although we will see that the definition of irreducible and prime becomes the same in a unique factorization domain. But initially, we should rigorously call these irreducibles, not primes. We have formed an irreducible factorization, although yes, later on it will be okay to call this a prime factorization of the element in the unique factorization domain. But initially, we should call it the irreducible factorization. We factorize this element into a product of irreducibles here. Okay, so again I'll stress that if your element was a unit, then you'll have absolutely none of these irreducibles. It'll just be that the element is equal to whichever unit it actually is. So it'll be a really trivial factorization in that case. But for elements that are not units, you will have some irreducibles appearing here. Now, there's something else to add here. This factorization of a non-additive identity element into irreducibles in this way is unique up until a certain point, and it's unique up until the fact that you can use different associates of these irreducibles in each of these places. So let me explain in more detail what I mean by this. Okay, this P1, let's say here, we could replace it with some unit times an associate of it. Okay, so what I could do is I could take P1 here and write it as, let's say, some unit which I'll call U1 times P1 bar, where P1 bar is an associate of P1. Okay, so for instance, I could have U1 here as the negative 1 element of my unique factorization domain, and then P1 bar would be negative P1, the additive inverse of it. Okay, and those two would multiply together to give P1. I could then substitute this thing in for P1 here. Okay, and then I'd have U1 to the power of U1 times P1 bar. So we'd have U1 times P1 bar here, all to the power of alpha 1. Okay, and of course that would be equivalent to U1 to the power of alpha 1 times P1 bar to the power of alpha 1 because of the commutativity of multiplication. Okay, and then we could just pull the U1 to the power of alpha 1 forward into this unit portion, because when you multiply lots of units together in a ring, you will still end up with a unit, so we can pull that into the unit portion. But now we have changed this irreducible factorization here, because instead of having row 1 appearing in the irreducible factorization, it would now have row 1 bar appearing there, and the unit might well be different as well. Okay, so up until that point that you can use different associates of the irreducibles in your irreducible factorization here, it is unique. So it's unique up until that point. The other important thing to say here, and I will make this clear when we actually do an example of this, okay, is that although you could write a irreducible factorization where you have multiple different elements in the irreducible factorization which are associate to one another, okay, it would not be idyllic to do so. Okay, so what I'm saying is that you would ideally only have one associate element appearing in this irreducible factorization. So ideally you would not have a power of P1 appearing in this irreducible factorization and a power of P1 bar appearing in here. So you wouldn't want it like this. You wouldn't want to have on the end here some power of P1 bar as well. Okay, so maybe just one P1 bar there. You wouldn't want to have two elements that are associate to each other appearing in this irreducible factorization. We haven't proved that we can call it a prime factorization yet. Okay, so you wouldn't want to have elements which are associate to each other appearing here. You could have them, okay, but why not make sure that you use the same associate all the time? Why not be consistent in that way? There's no reason to make it messy and have two elements that are associate to one another but fundamentally are different elements in the ring appearing in the irreducible factorization. Okay, right, so I think all of this will become a lot clearer when we actually do an example. So let's now move on to examples. Okay, so Firstly, I'm going to stay abstract, but then don't worry, we will do a concrete example of this. Okay, so examples then of unique factorization domains. So the first trivial example of unique factorization domains are fields. All fields are unique factorization domains, and they are trivially unique factorization domains. And the reason they are trivially unique factorization domains is that fields consist of an additive identity element along with loads of other elements which all have multiplicative inverses. So apart from the additive identity, all elements in a field are units. Okay, so that means that when we create their irreducible factorizations, they will just have the irreducible factorization f for an element of a field is just equal to itself. That will be its irreducible factorization. Put more bluntly, there are no irreducibles in a field, okay, because an irreducible needs to be a non-additive identity, non-unit element, okay, and there are no such elements in a field. So these irreducible factorizations are very, very simple in fields, and they certainly trivially obey the criteria for a unique factorization domain. Okay, so all fields are trivially unique factorization domains. Less trivially, we're going to see that all principal ideal domains, okay, which are integral domains in which all of the ideals are principal ideals, all principal ideal domains are actually unique factorization domains. Now, I'm not going to show that at the moment. That's going to be something we show right at the end. Okay, and it's a reasonably involved proof. It's not a totally trivial proof. Okay, now, what that is going to mean is that all Euclidean domains are also unique factorization domains. So I can add on now Euclidean domains, because all Euclidean domains are principal ideal domains. So if all principal ideal domains are unique factorization domains, then all Euclidean domains are going to be unique factorization domains. Okay, so we can draw now a nice picture like so, okay, where we show the sets of unique factorization domains, principal ideal domains, and Euclidean domains. So this big bubble out the side, this will represent all of the unique factorization domains, the UFDs. This smaller bubble inside, this will represent all of the principal ideal domains, the PIDs, and this one right in the center here, this will be the Euclidean domains. Okay, so we've discussed previously that all Euclidean domains are principal ideal domains, but not all principal ideal domains are Euclidean domains. Okay, now the same relation holds true for principal ideal domains and unique factorization domains. We're going to show that all principal ideal domains are unique factorization domains. What we're not going to show, but which is true, is that not all unique factorization domains are principal ideal domains. So this bubble diagram does show the relationship correctly. Okay, the UFDs, the set of all unique factorization domains, is bigger than the set of all principal ideal domains, which I'll colour in orange here, which is itself bigger than the set of all Euclidean domains, right at the centre there. Okay, right, so we will go on to prove that all principal ideal domains are unique factorization domains at the end of this video. Now, what I want to do before that, however, is do an example. Use the classical example, okay, which is the ring of integers. Now, of course, we know that the ring of integers is a Euclidean domain, so it's a principal ideal domain, and from this picture, I can now say that it is, in fact, a unique factorization domain, but we haven't proven that yet, but we will, okay? Now, in the integers, you can factorize all of the non-zero elements into an irreducible factorization. Now, we don't call it an irreducible factorization, we call it a prime factorization. And one of the things that I'll show you after this is that primes and irreducibles, the definitions of those two, are utterly interchangeable in the context of a unique factorization domain, which is why we can call this a prime factorization very soon, but at the moment we should stick with calling it an irreducible factorization. Okay, let me just give you then an example of an irreducible factorization in the integers, and I really want to stress this point that you can change to using different associate elements, because you might never have thought about that when you were doing this classically. Okay, so I want to highlight some of the more difficult to understand points about this. So let's do an example of factorizing some integer down into its irreducible factorization. Okay, so remember the units in the integers are only -1 and 1. They're the only two units in the ring of integers. Okay, they're the only two elements that have multiplicative inverses. Okay, right, that will be important for us to consider. Okay, so let's take an element and let's form its irreducible factorization then. So let's take the element 132. Okay, an arbitrary element here. Now, let's write out its irreducible factorization. So hopefully you remember how to do this from school. Okay, so what we can do is let's firstly split it into 2 times something. So what is the other thing? Okay, so we'll need 2 times 60 is 120, so it looks as though it's going to be 2 times 66 here. Okay, so the first thing I've done is split this into 2 times 66. Now let's split 66 into 2 times 33. And then let's split 33 into 3 times 11. Okay, so we'll get 2 times 2 times 3 times 11. And all of those things are prime numbers in the integers, and therefore they are irreducibles. Because remember, really we use the word prime when really we should use the word irreducible in the context of the integers. We do that obviously for historical reasons. Okay, so 132 is written as 2 times 2 times 3 times 11, which are all irreducible elements in the integers. So I found a nice irreducible factorization here. Okay, so I'd write this even nicer as 1, there's my unit out the front, times, and then I'd have 2 to the power of 2 times 3 times 11, like so. Okay, so these are my irreducibles. So I could call 2p1, 3p2, 11p3, and then alpha 1 would be 2, alpha 2 would be 1, alpha 3 would be 1 as well. And then out the front here, this is my unit. Okay, so here is a irreducible factorization of 132. What I want to show you is that it's unique up to the point that you can use different associates for these elements. So what are the associate elements in the integers? So if I have an element A, an arbitrary element in the integers, what's its associate element? Well, they'll just be all things of the form a unit times A. So you'll multiply 1 by A and that will give you A. The other one that you'll get is negative A. So A and negative A are associate elements in the integers. Okay, so let's now replace some of these with their associate elements. So for instance, I could replace in here 2 with negative 2. Okay, and it wouldn't actually change the unit I need out the front because the squaring would cancel the negative. Okay, so I'll have negative 2 squared times 3 times 11. There is another irreducible factorization, and this is why I wanted to do an example, because in school you probably wouldn't even have considered this a prime factorization, but now we're grown up, this is another equally valid factorization. Okay, into irreducibles. Okay, so that's another one, a different one to this, but we know that it's not so different because all we've done is change the associate element that we're using in this position here. Okay, but we could go further. We could say let's move 3 around, let's change 3 into negative 3 as well. So we could write another one here, so we'll have negative 2 squared still, and then we'll have times negative 3 times 11 here, and then of course what we'd have to do is change the unit out the front. Now the unit we'd have to have here would be negative 1. Okay, so there's another example of a different irreducible factorization, but it's okay because all we've done is change the associates that we're using and change that unit out the front. Okay, so that's what I mean that the irreducible factorization needs to be unique up to the fact that you can use different associates of the irreducibles, and then you can mess around, you can play around with the unit that you need out the front. Okay, right. Now the other point that I wanted to give is that when you do one of these things, it would be silly to use different associates in the actual irreducible factorization. So let me give you an example of this. So if I wanted to do this, I wouldn't for instance, make this 1 times 2 times 3 times 11 times negative 2. Okay, I could, that would still be an irreducible factorization, but it wouldn't be an idyllic one. Okay, because look, I've used different associates here. Okay, these are our two associate elements here. Oh, and I've made a terrible mistake as well. I'd have to change the unit here to -1. Okay, so here is the unit, and here are the irreducibles. But here I have now used two different associates, or two associate elements at different points in this factorization. I wouldn't advise you to do this, okay? And in some of the theorems that we're going to do, we will assume that you haven't done this. We will assume that you have picked your unique factorization carefully, okay, so that you only have one of each associate being used, okay, so that you don't have 2 and -2 appearing at different points here. You see, in all of these are sensible ones because we've used the same associate, okay? We've used 2 here twice, we've used -2 here twice, we haven't used 2 and -2 separately. Of course, this problem doesn't arise for 3 and 11 because they only appear once, okay? So you can't have the option of using 3 at one point and -3 at the other point. But where you do have irreducibles appearing more than once, you have this option of then, do I use different associates at different points? Don't do that, is my advice. Okay, pick your factorization into irreducibles sensibly so that you only use one of each associate in your irreducible factorization. So that was what I was trying to communicate at the end of my discussion. Okay, that you would choose your factorization into irreducibles sensibly. You wouldn't have it like this. You'd have one of these, not one of these. Okay, right, so there's the basic introduction then to unique factorization domains and what they are. Let's now do the proof that prime and irreducible mean exactly the same thing in a unique factorization domain, so that I can stop calling this thing an irreducible factorization and start calling it a prime factorization. Okay, so what we want to prove is that prime and irreducible are equivalent. Okay, now, hopefully you should be familiar with the fact that showing that prime implies irreducible is very, very easy, okay, because we've already done it in the previous video in this playlist on ring theory. We have shown in the video on primes and irreducibles that in an integral domain, a prime element is automatically an irreducible element. So if you're a prime element, it implies that you are irreducible if we're working in an integral domain. Now, since a unique factorization domain is an integral domain, that was the first line that I put there, okay, we can conclude that all prime elements are irreducible elements. Now, the key thing then is to show the other way round, to show that all irreducible elements are also prime elements. That's the new bit, okay, and then if we've got both of these, then we can conclude that prime and irreducible can be used completely interchangeably. They're the same thing in a unique factorization domain. Okay, so let's do this then. So let's take some irreducible elements. So let's say P here is an irreducible element. What we now want to show is that it satisfies the definition of a prime element. Now, what is the definition of a prime element? The definition of a prime element is that when we generate its principal ideal, we must get a prime ideal. Now, the first thing to say is that if P is an irreducible element, then it's not going to be equal to 0, okay, and it's not going to be equal to a unit. Remember, that's part of the definition of an irreducible. Okay, so when we generate the principal ideal, we're not going to get the 0 ideal, and we're not going to get the unit ideal, and that's good because actually I missed a bit out on the definition of a prime. A prime is something which generates a non-zero prime ideal. Okay, so it's good that it is not generating the 0 ideal. Even though you do think of the 0 ideal as a prime ideal, the 0 is not considered as a prime number, even though its ideal that it generates is a prime ideal. Okay, so it's good that this is not 0, basically. The other thing it's good is that it's not a unit, because of course the unit ideal is not a prime ideal, because prime ideals are proper ideals. Okay, so what we now want to show is that this is indeed going to be a prime ideal. Now, what does it mean to be a prime ideal? Well, it means that you're a proper ideal is the first thing, And secondly, it means that if you multiply two elements together and get something within this ideal, it must imply that one or both of the elements that you multiply together are already in this ideal. Okay, so what we need to prove is that if we have A and we multiply it by B and get something that's in this ideal, and something in this ideal is of the form S times P, okay, where A, B and S here are all just elements of the ring, okay, so I've multiplied two things together and by assumption I've got something in here, okay, that's of the form S times P. What I need to now show is that either A is already in here or B is in here. So to show, okay, that A or B is an element of this ideal. That's what it means to be a prime ideal, that whenever you multiply two things together and get something within the ideal, one or both of those things that you multiply together must be in the ideal already. Okay, so how are we going to show that? Well, this is absolutely going to come down to the way in which these factorizations into irreducibles work when you multiply two things together. Okay, so what I want to consider is what is the irreducible factorization going to be of this product S times P? Okay, well my claim is that when you multiply two elements in a unique factorization domain together, their factorizations into irreducibles just multiply together. So this will have a factorization into irreducibles, this one has a very trivial factorization into irreducibles because it is just an irreducible, so its irreducible factorization will just be itself. Okay, of course you could come up with more complicated ones involving a unit times an associate, but why would you? Okay, so that one has a very simple irreducible factorization, and then this one could have a more complicated one, but you're just going to combine them together. So let's say S had this complicated factorization here, a unit times P1 to the power of alpha 1 all the way up to Pn to the alpha to the n. The factorization into irreducibles of S times P is then just going to equal this multiplied by P. Okay, so S times P is just going to have factorization into irreducibles, and let me just move this up, equal to this unit times P1 to the power of alpha 1 all the way along to Pn to the power of alpha n, and then you'll have P on the end. Now that may seem so trivial, but it's the crux to everything in this proof. Okay, the understanding that when you multiply two elements together, the irreducible factorizations just combine basically. You just multiply all of the irreducibles and then you've got a new irreducible factorization. Okay, and that is so important. Okay, so on this side then, our irreducible factorization will contain this irreducible P here. Now, go to the other side, we've got A multiplied by B. Okay, the irreducible factorization of this is just going to be the irreducible factorization of A times the irreducible factorization of B, and that must equal this thing. Okay, so if we multiply the irreducible factorization of A with the irreducible factorization of B, it must give me this combination of irreducibles here. Okay, now what does that mean? Well, the only way that you would get P appearing in your irreducible factorization of A times B is if P appears in one of the irreducible factorizations of A or B, or at least an associate of P appears in the irreducible factorization of A and B. And then by messing around with that irreducible factorization a bit, I could get P to appear in the irreducible factorization. So what I can now conclude is that P had to appear in the irreducible factorization of A or B. It's so simple, and yet it is very important that you appreciate and understand this, okay, because what we're doing is actually quite amazing here. It just seems deceptively simple, okay, but we are using completely the unique factorization domain structure here. Okay, so now what we can conclude is that either A or B has this P appearing in its factorization, or at least even if in the form that it was originally and it didn't have it, it would have an associate appearing in it, so we could meddle around with it a bit to get P appearing there. And when P appears in the factorization of one of these two, that'll mean that one of these two is just a multiple of P, and therefore it'll appear in the principal ideal generated by P, and therefore we have successfully shown that one of these must be in the principal ideal generated by P. Okay, and there we go. Now, I should stress that there's another case to this. This is almost like case 2. I should have probably put a case 1 here. So this is case 2, okay, where we assume that S has this irreducible factorization here. There is another case, okay, which is case 1, which is that S could be equal to 0. Now, if S is equal to 0, then of course S times P doesn't look like this, it just looks like 0. Okay, but that would mean that A times B was equal to 0, and because we're working in an integral domain, that would then imply that A or B was equal to 0, and therefore one of them would be in this principal ideal generated by P, because 0 is in the principal ideal generated by P always, because 0 times P will equal 0. Okay, so case 1, S is equal to P, therefore A times B would equal 0, which therefore implies A is equal to 0 or B is equal to 0, because our unique factorization domain is an integral domain, okay? And then what we can conclude, therefore, is that either A or B is in the principal ideal generated by P. Okay, so either, whichever one of these is true, one of them, A or B, will have to be in the principal ideal generated by P, because 0 is in the principal ideal generated by P. Okay, so that's one of the cases that we can have here, which is that A times B is equal to 0, and 0 is obviously an element of this principal ideal generated by P, but in that case A or B will have to equal 0, and therefore it will be an element of the principal ideal generated by P. The more interesting case is that S doesn't have to equal 0, because this A times B is non-zero. Okay, and then we can conclude this, that either A or B in its irreducible factorization must have had P appearing there, and therefore must have been in the principal ideal generated by P. Okay, but that is important to add case 1 onto this proof. Okay, right, so what we have now shown then is that if you have an irreducible element in a unique factorization domain, you can conclude that the principal ideal generated by it is a non-zero prime ideal, and therefore it obeys the criterion for being a prime element. Okay, so if you're an irreducible element in a unique factorization domain, you are a prime element. So primes and irreducibles are completely the same in a unique factorization domain. Okay, so you don't actually need to be a principal ideal domain for it to be the case that primes and irreducibles are the same thing. In the video on primes and irreducibles, we show that indeed in a principal ideal domain, primes and irreducibles are the same thing, but looking at this picture, we've now got a weaker criterion. You just have to be a unique factorization domain. Remember, principal ideal domains are a subset of unique factorization domains. So in all unique factorization domains, primes are the same elements as irreducibles. Okay, so we can now use the two terms interchangeably, even though in an arbitrary commutative ring they are not necessarily the same thing. Okay, so we can now call this irreducible factorization a prime factorization, as we would more normally. Okay, so we'll have a break here, and in the next video what we'll talk about is greatest common divisors in unique factorization domains.